let's look at the power factor problem, power factor correction problem. The power factor in the real world, in the real practical system, very important, because if the power factor is low, that means in addition to supply the certain amount of the real power or the active power, you have to have a certain amount of Q to accompany these the reactive power. And remember, the reactive power will not help the system, right? The reactive power will cause the current to be higher than the system with the higher power factor, and so the reactive power actually causes the higher current. The higher current has two sort of the negative impact on the real system. One is because the higher current, that means it will occupy the capacity. Because if you think about the line, the transmission line or the distribution line, and this line, for certain wire gauge, it can only carry a certain amount of current, right? So if the current is too high, that means the line may be getting too hot, and it can cause a fire, so on and so forth. So it's very you have to have increased capacity to accommodate this increased current capacity, the current values. And the second one is we also know each line has resistance, right? So if for higher current, and then the power loss in the line in the either transmission or distribution and will increase. So both in terms of the investment are going to be higher, or the operational costs are going to be higher as well. So typically we don't want the load power factor too low. If it's too low, we want to bring this back closer to the unity power factor, which is the power factor equal to 1.0, right? And in order to do that, and the typical way of doing that is the so-called power factor correction is to parallel with the load, parallel the load with a capacitance if the load power factor is lagging, right, or the load is inductive. And in the practical system, that's most of the scenario. Very rare case you have the power factor is away from the unity, but it's a leading power factor. That's very rare, because that's the system. The practical system is mainly made of the inductance, the inductance and the resistance. And so we're going to look at the very simple example. In the real world, things could be a little bit more complicated, especially you're talking about the system interconnect, and you're trying to compensate the power factor and correct the power factor at a certain spot, right? And sometimes we also call the power factor correction as the reactive power compensation. And reactive power compensation is more broad compared to the power factor correction. And the reactive power compensation also sometimes just to keep the voltage level high, and it's slightly broader issue. So let's look at this example here. The example here is I have this load impedance. So I'm kind of making this example a little bit simplified. I drop this line impedance there because if you don't have the line, if you keep the line impedance, the problem is a little bit more complicated. Okay, unless we reframe the problem. Okay, and so let's see the load. I have a load impedance this by L that absorbs the 5 kilowatts. So this is the same as before. And this VS has this equal 120 volts RMS value. And so the frequency, we need the frequency in order to determine the capacity value. We'll see soon. And we try to find the capacity values that will correct the source power factor, or the power factor at the source, and also the power factor of combined this load impedance this by L and the capacitance, and to improve that power factor from the 0.8 of the load only to the combined 0.95. So the source will not need to supply that high reactive power. Okay, so let's see how we're gonna go about this. So one thing I should mention that when you are adding the capacitance, you're not doing anything to the active power, right? The active power 5 kilowatts, as long as the voltage stays the same, that's the reason I dropped the line impedance. As long as the voltage stays the same across the load, so the load will draw that 5 kilowatts, right? So let's start with the problem. So we're gonna still use the principle of the power conservation. The real power, here we don't really need to do much. So we're looking at the power conservation of reactive power. That means the QS. So the QS supplied by the by the source, and so the QS. So I hope the notation will make sense. So the QS would be equal Q sub L plus Q sub C. So this is the Q sub L. This is the reactive power absorbed by the load impedance. Q sub C is reactive power absorbed or delivered to the capacitance. And we would expect this would be a negative value, right? The QS would be the power, the reactive power absorbed by supplied by the source, right? So therefore we can calculate this, and the QS is equal to the QS would be equal to the S sub S, the apparent power, times 1 minus PF square, right? And since this is still lagging, so we're gonna have the positive QS. So this lagging, that means QS is positive. And so therefore we have the P sub L. Remember the real power delivered by the source is going to be still equal to the real power absorbed by the load impedance, because the capacitance does not absorb any real power, right? So therefore we can use P sub L divided by PF. Here we use the S, right, times square root of 1 minus PF. So this is the power factor at the source or the opposite of the source. So we get a 5,000 divided by 0.95, not 0.85, 0.95 times square root 1 minus 0.95 square. And I calculate this, calculated beforehand, that's going to be equal to 1.64 kilovolts. Okay, so for the QL, we calculated QL before, and the problem didn't really change. So therefore, QL is going to be equal P sub L over PF, the load power factor times 1 minus PF sub L square, and that's still going to be equal to 3.10 kilovolts. And so therefore, the QC is going to be equal QS minus Q sub L. As expected, it's going to be a negative number, and that's equal negative 1.455 kilovolts. Okay, and now we calculate the amount of reactive power delivered to the capacitance. And we also know the one way to calculate this complex power. Let's see, S sub C is equal. We know that's just equal J times Q sub C, right? Q sub C, and so because the P sub C is 0, right? So that's equal to the V, in this case, we're gonna the VS, right? The VS is gonna be the voltage across the capacitor as well. So we're gonna use VS square divided by Z sub C conjugate. Remember, V times I conjugate, that's another way of calculating this, because of the V times I conjugate, I is equal V over Z. So therefore, the complex power is V times V conjugate over Z conjugate. So therefore, we have V squared magnitude, and then we have that's equal Vs square over, and the Z sub C is 1 over J omega C. The conjugate of this is going to be negative, right? So let me write it in 2 steps. So this is going to be the conjugate, that's going to be equal Vs. The conjugate is, actually now I can combine these two this way, and that's going to be equal minus Vs squared times J omega C. So therefore QC is going to be equal Vs squared times omega C, right? And so therefore we calculate the QC and a negative sign here, don't forget about that. So the C is going to be equal, if you calculate something you get a negative capacitance, you know that there must be something wrong there, okay? So far I don't think there's negative capacitance exist in the real world. So we have a QC, negative QC over Vs squared times omega, and remember omega is just 2 pi times the f, right? So let's plug in the numbers. So I have a negative 1455 divided by 120 squared times 2 pi times 60 hertz. That's the reason we need 60 hertz. If I calculate the number, it should be 261.8, 268.1 microfarad. So this is the capacitance we need to correct the power factor to 9.95. Okay, so that's the second topic of the power factor correction. So this concludes this lecture with these 2 short videos. Remember, no matter what you do, just keep going, right? So we are very close to the end of the semester. We need 3 more lectures. That's it. Okay, I'll see you next time.